some of the numerous different celestial bodies dispersed across the endless expanses of the cosmos, some that are as close to our home planet, have been preying on human minds ever since it was discovered that there were other worlds out there that were suitable for life. Scientists have discovered thousands of planets beyond the solar system, but the majority of them are completely different from Earth, until now. Let's find out. The Earth Similarity Index, ESI, also abbreviated as ESI, is a metric that was developed by scientists and is based on a number of essential criteria, such as a planet's atmosphere in terms of its density and temperature. This combination can be used to estimate many different aspects of an object, including its mass, chemical makeup, gravitational level, and atmosphere. Additionally, it helps determine whether the surface of the planet is covered in liquid water or not. The Earth is used as the benchmark for this index because its parameters are typically considered to be ideal. The Similarity Index of Earth, which is also 1, serves as the foundation for the ESI value. There are 3 overarching categories that can be used to classify everything that we know about the world. The first category contains things like gases and ice giants in addition to things that are extremely hot or extremely cold, which have an ESI score of less than 0.5. Even if only one of the characteristics of a body in the solar system exceeds its maximum allowable value, the conditions of a celestial object become unfavorable for the emergence and continued existence of life. Consider the planet Venus, which is comparable to Earth in terms of its radius and mass, but has a much higher average surface temperature than our planet because it's closer to the Sun and has a thicker atmosphere. Celestial objects that fall into the second category have an ESI that ranges between 0.5 and 0.7. The majority of these worlds are composed of rocks and have temperatures that are on the cooler side, but they can also be ocean worlds or even some large satellites of Earth. These worlds are similar to Earth in more ways than one. In fact, having a high Earth likeness index does not ensure that the conditions are favorable to life. Low-mass planets, for instance, frequently aren't able to keep an atmosphere that's dense enough to support life, and their magnetic fields aren't strong enough to protect the surface of the planet from radiation that can cause fatalities. It's possible for other celestial bodies to be located in such close proximity to their parent star that they end up becoming tidally locked. Obviously, the existence of all these obstacles drastically decreases the likelihood that life ever existed. The incredible world was found to have originated from a tiny red dwarf that was given the name Teegarden B in 2003. This star is so faint that it cannot even be observed with the naked eye, despite the fact that it is situated relatively close to the planet Earth. The mass of the star is only 9% of that of the Sun, and its radius is only 5% larger than that of Jupiter. As a result of the internal thermonuclear reaction of the star only being barely sustained by gravitational forces, the surface temperature of a red dwarf is only 2,900 Kelvin, which is equivalent to about 2,630 degrees Celsius. This is the same as the surface temperature of all other red dwarfs. It has a relatively small habitable zone and is situated relatively close to Teegarden's star. Both of these exoplanets have nearly perfect circular orbits with radii of 0.045 astronomical units. One of these planets is located beyond the star's habitable zone, and the other is located beyond the orbit of the outer planet. Both of these planets were found in the star's system in 2019. Completes one orbit around the Sun every 11.5 days. Due to the low luminosity of its parent star, the planet's surface temperature is extremely inhospitable. Despite the fact that its radius is estimated to be approximately 3.5% larger than that of our planet, the exoplanet is only 5% larger than our own planet in terms of both its mass and its radius, which indicates that its gravitational value is also quite close to what we are accustomed to on Earth. As a result of this, it is reasonable to hypothesize that the core of the exoplanet is composed of a massive metallic core that is encased in a thick layer of mold and silicate mantle that is on the centimeter scale. The fact that the surface temperature of the planet is 28 degrees Celsius, higher than that of Earth, means that it can shrink to half its size while still retaining liquid water, and that the temperature profile of the planet is suitable for the majority of microorganisms. The radial velocity method, which is used to detect extrasolar planets like Teegarden B, is insufficient to obtain any information about the composition of the atmosphere of these planets. Because of this, it is important to keep in mind that the temperature distribution of a planet is directly influenced by its atmosphere. For instance, A planet with a dense atmosphere that contains a high proportion of methane and carbon dioxide will have a higher average temperature. Because of its location so close to its parent star, this celestial body, as fascinating as it may be, is not without flaws. As mentioned earlier, Teegarden B is always facing its star in the same direction, which causes temperature differences between the day side and the shadow side of the body. This red dwarf star has a propensity for suddenly increasing the amplitude of the amount of light that it emits. As I have already mentioned, the number of new worlds discovered in the last 20 years has been hundreds of times greater than in the entire history of observations, and one can't help but think that soon the long-awaited seeds of Somalian life will be discovered in some corner of the universe. Thanks to technological advancement, the number of new worlds discovered in the last 20 years has been hundreds of times greater than in the entire history of observations. What do you think about these new exoplanets? What will this mean for humankind in the future? In recent years, the discovery of exoplanets has sparked intense curiosity and excitement among scientists and the general public alike. These planets, which exist outside our solar system, are often located in faraway star systems, some of them hundreds or even thousands of light-years away from Earth. One of the most remarkable aspects of these findings is the sheer diversity of exoplanets. Some are gas giants similar to Jupiter, while others are rocky, terrestrial planets with conditions that may potentially harbor life. One important aspect of this research is the search for planets within the so-called habitable zone of their stars. The habitable zone, also known as the Goldilocks zone, is the region around a star where conditions are just right for liquid water to exist on the surface of a planet. Water, being essential for life as we know it, is a crucial factor in determining whether a planet can support life. However, the presence of water alone is not enough to guarantee the existence of life. A planet must also have other factors, such as a stable atmosphere, a magnetic field to protect it from radiation, and the right chemical composition to support the development of complex organisms. Astronomers are using increasingly sophisticated methods to detect and study exoplanets. The most common method is the transit method, which involves monitoring the brightness of a star as a planet passes in front of it. When a planet transits its star, it causes a small dip in the star's brightness. By measuring the amount of light blocked, astronomers can determine the size of the planet and its orbit. The radial velocity method, which I mentioned earlier, is another widely used technique. It measures the tiny wobble in a star's movement caused by the gravitational pull of an orbiting planet. The Kepler Space Telescope, launched in 2009, revolutionized our understanding of exoplanets. Over the course of its 9-year mission, Kepler discovered more than 2,600 exoplanets, many of which are in the habitable zone of their stars. Kepler's successor, the Transiting Exoplanet Survey Satellite, TESS, is continuing this work, focusing on finding smaller, rocky planets that are more likely to be similar to Earth. TESS has already discovered thousands of new exoplanets, some of which could potentially be habitable. As we discover more exoplanets, we are also beginning to learn more about their atmospheres and compositions. Using instruments such as the Hubble Space Telescope and the upcoming James Webb Space Telescope, scientists are able to analyze the light passing through the atmospheres of exoplanets. This light can reveal information about the planet's atmosphere, including the presence of gases such as oxygen, methane, and carbon dioxide. These gases are of particular interest because they are often associated with biological activity on Earth. For example, oxygen is produced by photosynthesis, and methane is a byproduct of digestion in animals. In some cases, scientists have even been able to detect the potential for life on distant planets. In 2020, researchers announced the discovery of phosphine in the atmosphere of Venus, a gas that on Earth is primarily produced by microorganisms. While this discovery was met with excitement, it is still unclear whether the phosphine is the result of biological activity or some other unknown process. Further observations and research will be necessary to determine the true cause of the phosphine signal. The search for life beyond Earth is not just about finding planets that could potentially harbor microbial life. Many scientists are also interested in the possibility of discovering intelligent alien civilizations. One of the most famous efforts in this regard is the search for extraterrestrial intelligence, SETI. which aims to detect signals from advanced alien civilizations. While no definitive signals have been detected so far, SETI researchers continue to scan the skies for unusual radio waves or other signals that could be the result of intelligent life. In addition to the search for life, the study of exoplanets also has important implications for the future of humanity. As our planet faces increasing challenges such as climate change, overpopulation, and resource depletion, the idea of finding another habitable planet has become more appealing. If we could identify a planet that is similar to Earth and within a reasonable distance, it could potentially serve as a backup location for humanity in case of disaster on Earth. Of course, this raises many questions about how we would travel to such a planet and what kind of technology would be required for interstellar travel. The concept of space colonization has been a topic of science fiction for centuries, but recent advances in space technology are bringing it closer to reality. Companies like SpaceX, led by Elon Musk, are developing rockets capable of carrying humans to Mars, and there are even plans to establish a permanent colony on the Red Planet. While this is a significant step forward, Mars, with its thin atmosphere and lack of liquid water on its surface, is far from an ideal location for human habitation. Finding a more Earth-like exoplanet could offer more promising opportunities for space colonization. In the long term, space exploration and the study of exoplanets could provide answers to some of humanity's most profound questions. Are we alone in the universe, or is life common throughout the cosmos? How did life on Earth begin, and are there other planets where life may have evolved in similar ways? These are questions that have fascinated philosophers, scientists, and ordinary people for millennia, and the discovery of exoplanets brings us closer to answering them. As our knowledge of the universe continues to expand, it is likely that we will continue to find new and exciting worlds. Some of these exoplanets may be similar to Earth in ways we cannot yet imagine, and they may hold secrets about the origins of life that we have yet to uncover. The discovery of alien life, whether microbial or intelligent, would undoubtedly be one of the most important milestones in human history, and it would radically change our understanding of our place in the universe. The exploration of exoplanets not only offers us a chance to discover new worlds, but it also provides an opportunity to enhance our understanding of the fundamental processes that govern the formation of planets, stars, and galaxies. By studying these distant worlds, scientists can better understand the diversity of planetary systems and how conditions on different planets might vary. For instance, some exoplanets may exist in star systems that are much older than our own, providing a window into the evolution of planetary environments over billions of years. Others may be in younger, more dynamic systems where planets are still forming, which could shed light on how planets like Earth came into being. One of the key challenges in exoplanet research is determining whether a planet has conditions suitable for life. To tackle this, scientists are focusing on a variety of factors beyond just the presence of liquid water. For example, the size of a planet is crucial for determining whether it can retain an atmosphere that might support life. Planets that are too small may not have enough gravity to hold onto their atmosphere, while larger planets could have atmospheres that are too thick and dense, preventing the conditions necessary for life. The composition of the planet's atmosphere is another critical factor, as it can reveal whether a planet has the right chemical building blocks to support biological processes. Another interesting area of study is the phenomenon of rogue planets, planets that do not orbit a star at all. These planets are ejected from their original solar systems or form in isolation. Rogue planets are particularly intriguing because they may harbor subsurface oceans beneath their icy crusts, which could be a potential environment for life. Even without a nearby star, these planets could maintain warmth through geothermal activity, possibly creating conditions where life could exist in a completely different form than what we experience on Earth. As the study of exoplanets continues to advance, scientists are also looking to the future to develop new technologies that will enable even deeper exploration of distant worlds. One promising avenue is the development of space telescopes that can directly image exoplanets. Current methods, such as the transit and radial velocity techniques, provide indirect evidence of planets, but direct imaging would allow scientists to study exoplanets in greater detail, analyzing their atmospheres, climates, and even potential signs of life. In addition to direct imaging, the possibility of sending probes or spacecraft to distant exoplanets is a long-term goal. While current technology makes interstellar travel impractical, there are concepts in development that may one day make it possible. For instance, initiatives like Breakthrough Starshot aim to send small, lightweight probes to nearby star systems using powerful lasers to propel them at a fraction of the speed of light. These probes could provide invaluable data on exoplanets in other star systems, opening a new era of exploration beyond our solar system. The ongoing search for habitable exoplanets also raises important philosophical and ethical questions. If we were to discover a planet with conditions similar to Earth, should we attempt to colonize it, or should we leave it undisturbed? What responsibilities do we have to protect any potential ecosystems that might exist on these distant worlds? These are questions that humanity will likely face as we continue to expand our presence in space and consider the long-term future of our species.